Hi, this is the beginning of a new course on number theory. In this course, we are going to go into the details of number theory, all of the theorems, the ideas, problem solving techniques, and basically a lot of practice problems. So we'll begin by talking about linear congruences. So the first thing is basically understanding what a congruence is. So if A is congruent to B mod M, what that means is that M divides B minus A, right? So basically B minus A should be equal to some M times K, where K is an integer. K belongs to Z. That is the basic idea of congruences. And you might be familiar with some properties of congruences. Like if A is congruent to B mod M, there is a reflexive property. So B will be congruent to A mod M. There is also transitivity. A is congruent to B mod M implies, and B is congruent to C mod M implies that A will be congruent to C mod M. Obviously, we also have the reflexive property. So A will be congruent to A mod M. This is called reflexivity, this is commutativity, and this is transitivity. So congruence, the operation forms an equivalence class because it's an equivalence relation since it has the properties of reflexive, transitive, and commutative, right? This is theoretical stuff. We also know things like we can add numbers. If A is congruent to B mod M, that implies A plus minus C will be congruent to B plus minus C mod M, right? Similarly, you can multiply by some constant C. Here C is an integer, so we can add and subtract with a constant C on both sides of a congruence. Similarly, we can multiply by a constant C. AC will be congruent to BC mod M. That is also true. And you can even raise it to powers, like A power C will be congruent to B power C mod M. As long as A was congruent to B mod M and C is some fixed integer, right? The tricky part comes when we think about division. So if AD is congruent to BD mod M, it is not necessary, does not follow that A will be congruent to B mod M. Here D is some integer. It is not necessary that you can cancel out the D from both sides. The reality is that you can the real identity here becomes AD is congruent to BD mod M. That implies that A will be congruent to B mod of M by GCD of M and D. So this is the correct identity. Now, basically, if M and D are relatively prime to each other, if their GCD is 1, then we can cancel D from both sides of the congruence. From both sides of the congruence. So in that case, you can say that if AD is congruent to BD mod M, that implies that A is congruent to B mod M. Because this quantity becomes 1, the GCD of M and D is 1, so we can divide that and it is still same mod M, right? So this is very important. Division is important for us because it helps us solve linear congruences. So for example, let's do a few problems so that you understand the idea. We have to solve the congruence. In general, Rx plus S is congruent to T mod M. Here R, S, T, M are integers. And we have to basically find out the X which satisfies this congruence or linear congruence. It is linear because X has power 1 and we need to solve this equation. So the method is best explained with some examples. So I'll show you some. So for example, first one is you have 1233x plus 45 is congruent to 9090 mod 24. We have to find the x such that this quantity 1233x plus 45 is congruent to 9090 mod 24, right? Now, obviously, we have the property that we can add and subtract the same thing from both sides of a congruence. So what I will do in the first step is subtract 45 from both sides of the congruence. So I end up getting 1233x is equal to 9045 mod 24, right? So this is my new equation. Now since subtraction always works in congruences, right? Now if you think about it, uh, this number is divisible by 3 and this number is also divisible by 3, right? So I want to do division, but you remember that we cannot divide directly without thinking about the mod, right? So it is modulo 24. If you want to divide by 3, the modulo itself will change because 3 and 24, the GCD of 3 and 24 is 3, right? So I'm going to do division, but I'm going to do division carefully. So when I divide by 3, here, what do I get? I get basically 411x is congruent to, this becomes 3015 mod, this becomes 24 by GCD of 3 and 24 is 3, right? So I'm getting 411x is congruent to 3015 mod 8 now, correct? Now what we will do here is mod out the 8, like 411x, right? You can think of dividing by 8 because 411x can be written as 408x plus 3x, right? 411x is 408x plus 3x, but 408 is divisible by 8. So if you take modulo 8 on both sides, or at least modulo 8 here, this will be 0 mod 8 and this will be 3x mod 8, right? So if you mod out the 8, you can remove the big terms there. So basically this will convert to 3x mod 8, and on the other side 3015. If you divide by 8 3015, you will get 3, 7 and 3, 7, 6 and 7. You get 7 mod 8, right? You should get this value. So 3x is equal to 7 mod 8. This is what we are getting, right? Because 3015 I think will be equal to 8 into what? 361 and this is 7 and then 5. 5 you'll do by 6. So we'll get 48 plus 7, right? So that's how I'm getting 7 mod 8 taking remainders, right? So now my equation becomes 3x is equal to 7 mod 8. Now, how do I solve this linear congruence? 3x is congruent to 7 mod 8. So think about it. 7, if you add and subtract 8 to it, like 7 and 15 and 23 and 31, all of these are the same mod 8, right? So on the left hand side, you can say that 7 mod 8 is the same as 15 mod 8, right? Because it still leaves the remainder 7. The benefit of doing that would be you can write 3x is equal to now 15 mod 8 instead of 7 mod 8, right? I'm doing a plus 8 and I'm seeing when can I get a 15 so that I can cancel the 3, right? So what I'm saying is converting this equation to this equation by noting that 7 mod 8 is the same as 15 mod 8, right? And once you do that, you can now divide by 3 and x will be congruent to 5 mod 8 by GCD of 3 and 8. And GCD of 3 and 8 is actually 1. So you're getting x is congruent to 5 mod 8, right? So that is the solution of this linear congruence because now we are getting x can be anything like 8k plus 5, right? Any integer of the form 8k plus 5 or 5 mod 8 is the solution for the above congruence. So that was the solution there. Let's try a few more questions so that you get the idea. The next question is this one. You have 1235x plus 45 is congruent to again 9090 mod 24. So what are the steps? We can subtract both sides 45. That doesn't change anything. You can add and subtract anything in a congruence on both sides. So this becomes 9045 mod 24. At this stage, you can divide by 5 because 5 and 24 have GCD of 1. So it becomes 247x is equal to 1809 mod 24 itself, because 24 by GCD of 5 and 24, which is 1. So this is mod 24, right? Now we have mod 24 here and we have 247x. So we can again mod out using mod 24, because again, think about it, 247x is what? 240x plus 7x, right? So if you do mod 24 here, this part is divisible by 24. So it will become 0 mod 24. And this part will remain, which is 7x mod 24. So I'm just doing this operation mod out by 24. So you'll end up getting 7x, and 1809 when you divide by 24, what is the remainder? You'll get 9. 1800 is divisible by 24. So you'll get 9 mod 24. Now our only job is to remove the 7 from this equation. I need what is x, what is the congruence for x, right? So I don't need 7x. So how do I do that? I think of 9 mod 24, and what are the other terms? 9 will be congruent to 9 plus 24 or 33 mod 24, but 33 is not divisible by 7, so that doesn't help us. So again, it will be congruent to 33 plus 24, 57 mod 24, which is again not divisible by 7. Similarly, 81 mod 24 and then 105 mod 24, but 105 is divisible by 7, right? We can say 7x is congruent to 105 mod 24, and now I divide by 7 on both sides. Now 7 and 24 have GCD of 1, and therefore it doesn't matter, we can easily divide. X will be congruent to basically divide by 7, 15 mod 24, right? So my answer will be x is congruent to 15 mod 24. That is our answer for this congruence, right? Now let's do a slightly more complicated example. We will look at a simultaneous congruence, right? We want to solve the system of congruences, 3x is congruent to 4 mod 7, and 5x is congruent to 6 mod 9. 6 mod 9. Okay. So we want to find the x which satisfies both of these situations, correct? So think about this. 3x is congruent to 4 mod 7. So I can say it will be congruent to 4 plus 7, 11 mod 7, or congruent to 18 mod 7. 18 mod 7 is the same as 4 mod 7 basically. So we are getting 3x is congruent to 18 mod 7 from the first one, which becomes x is congruent to 6 mod 7. Notice that 7 does not change, because when you divide 7 by the GCD of 3 and 7, you are getting 1. So 7 by 1 is same as 7, right? So the solution of the first congruence is this: x is equal to 6, congruent to 6 mod 7. Now let's look at the second one. Here again, 6 mod 9, we can easily write as 15 mod 9. And we have 5x is congruent to 15 mod 9. And now divide by 5, you will get x is congruent to 3 mod 9, right? So basically what we are getting here is x is congruent to 3 mod 9 and x is congruent to 6 mod 7. We have to find a common x right here. So the idea here is x can be written as 7k plus 6 from here, and x can be written as 9m plus 3 from here. So we can say when are both going to be true simultaneously? So 9m plus 3 should be equal to 7k plus 6. And from here we can say 9m is equal to basically 7k plus 3. So 9m is congruent to 3 mod 7. This is what we are getting. When we try to satisfy both the conditions simultaneously, you're getting 9m is 3 mod 7. So this can be written as 3 plus 7, 10. 10 is not divisible by 9, plus 7, 17. So I'm saying 3 mod 7 is congruent to 10, congruent to 17, congruent to 24, congruent to 31, 38, 45 mod 7. Why do I stop at 45? Because I want to divide by 9 and 45 is divisible by 9. So I'm going to write this as 9m congruent to 45 mod 7. And now I'm going to divide by 9 on both sides, right? You can divide by 9 without changing the modulo because the GCD of 9 and 7 is actually 1. So this becomes m is congruent to, we are dividing by 9, so 5 mod 7, right? So we are getting m is 5 mod 7, so m should be 7p plus 5, something like that. And if we know the value of m, now we can say what was x, because if you recall, x was 9m plus 3, right? So if x was 9m plus 3 and m is 7p plus 5, so 9 into 7p plus 5 plus 3, right? So x is becoming 45 plus 48 plus 63p, right? So finally we have a solution. X is congruent to 48 mod 63. So that is how you solve a system of congruences or system of simultaneous congruences. Notice that your answer is congruent to mod of n1 and n2. If n1 and n2 were the initial congruences, the modulo of the initial congruences, right? This will be extended later into the Chinese remainder theorem. And basically, we will discuss that later when we come to it. For now, I wanted to discuss how to solve congruences and how to use the properties of basic congruences to solve linear equations. I hope you have understood what we have tried to show here. You should try a few problems. What we'll do in the next session will be solving quadratic congruences. Solving quadratic congruences, I want to discuss that as well. So that will be the topic of the next video. So that's it for now. I hope you learned something from this video and I'll see you next time.